Okay, so this is about week 5's assignments. So I have prepared few problems uh, from perturbation theory, stationary perturbation theory basically. So I'll try to solve them, and this will in turn help you to solve your week 5's assignments. All right. So okay, so let us start with that. So at any point, if you have any questions or any doubts, you can please ask. All right. Okay. So let us first look at this problem. The first one. Uh, so the first one is called momentum perturbation. So normally when you do perturbation, you see that there is additional potential which is a function of x, like you add another, like in a normal Hamiltonian there is some Vx, this is the total Hamiltonian, and you add some additional V of x, okay, which acts as a perturbation, which is small, very very small than the energy scales of the given Hamiltonian. But in this case the perturbation is added in momentum. So what do I mean by that? So like if this is our h naught, so we know all of the eigenvalues of h naught, so that means we know all of these states also. So now on top of this h naught we are adding a perturbation which only depends on momentum. So if that is the case, now we can derive the expression for the eigenvalues as well as the eigenvectors. Okay, so just to give you a little bit recap about perturbation theory. So normally when you do perturbation theory, if we let's say we are calculating the perturbative corrections to a nth eigenstate. So this goes something like this. So En is given by En naught. Okay, so En naught is the eigenvalue of my unperturbed Hamiltonian, so which is the eigenvalue of h naught, and there will be some term linear. So lambda here is the perturbation strength. Okay, my screen got stuck here. Okay, so 1 second. All right. Yeah, so I was talking about like how do we perturbatively calculate the corrections to the energy eigenstates. So in any perturbation is written in terms of the series like this, and this suffix, this denote the correction at which order we are calculating. So E1 is typically like given in terms of n, h prime and n, where I am assuming that this h prime is the perturbed Hamiltonian, the perturbation Hamiltonian, and then so this is my first order. So E2 on the other hand is something like n comma h prime m mod square divided by En minus Em, and there is a summation over m and n. Okay, and in this summation m is not equal to n, because if that is the case, then the denominator will go to 0 and this thing will diverge, this will become infinity. So that is not well defined. And similarly you can go on and calculate different orders. Okay, and similarly like you can also calculate what are the perturbative corrections to the eigenstates. Okay, so now like this is the main part of perturbation theory. So like let's say using this kind of formalism, let's try to calculate if our Hamiltonian h naught is given like that, for which we know all of the eigenstates, eigenvalues and eigen functions, and on top of that we are adding a perturbation which depends on momentum. Okay, so if that is the case, so derive the expression for the eigenvalues and the eigenvectors. Okay, so like a typical calculation of this form starts with like calculating a first order in energy. So what you will do is, you will, let's say you will plug in your psi like nth eigenstate. So I am writing the Kate notation here, nth eigenstate and then hp and then n. Okay, so you try to see that whether this is 0 or not. So if this is not 0, then you just calculate up to your first order and then be happy with it. But if this becomes 0, then you go on to calculate the second order term as well. Okay, so essentially what you want to calculate is the first non-zero perturbative correction. Okay, that is the most interesting thing, and we mostly calculate we mostly look out for that. But here this kind of, we do not need this kind of calculation, because we can try to be a little smart and try to look at this Hamiltonian before. So our total Hamiltonian is given in terms of p square by 2m plus some v of x plus lambda m by p. Okay, so here this lambda is a perturbative coupling, you can say also. So we will expand in terms of lambda. Lambda is very small than all of the energies in the of the Hamiltonian. So now we can try to see that if you can manipulate this Hamiltonian a little bit, can you simplify things a little bit? So let's first try to complete the square. Okay, so we see that there is a p square term, there is also a linear in p term, so we can try to add and subtract a few parts so that we can complete the whole square. So now let's try to do that. So 1 by 2m, I am taking this thing out and I am left with p square plus 2 lambda p. Okay, so now I have to add one part, p square plus 2 times p times lambda, and additionally I'll add another lambda square, and I'll also have to subtract it. Now I can complete this square and it becomes p plus the lambda whole square minus lambda square by 2m plus v of x. Okay, now you see that this Hamiltonian, this whole Hamiltonian after completing the square looks very much similar to the h naught we started with. So h naught was only this part, but now it seems like in the modified Hamiltonian, this p is just replaced by p plus lambda. And there is obviously one constant shift term. So if you just change, if you just add any constant number to your Hamiltonian, that doesn't change your eigenfunctions, that just shifts your eigenvalues, okay, by this much. So this is just a constant term and this doesn't change your expectation values, but this will change your, this will shift, basically give you a shift to your all of the energies. Okay, so like we see this kind of similarity, and then we try to come up with the eigenfunction that will reproduce its I mean, we will try to smartly find a eigenfunction for this also. Now like, so here from examining this Hamiltonian, we can try a few solutions. Okay, we can do some few hit and trial and see that do we get the eigenfunction. So if I change psi in x, like if I define a new psi tilde with e to the power I lambda x by h bar psi n x. Okay, so like, so this was the solutions of my h naught. Okay, and this is the additional phase term which depends on x. So these are the new things that I am adding, and I am trying to see that does this satisfy the eigenvalue equation or not. Now, so first of all, so the main change in our Hamiltonian is just this p plus lambda. Okay, so we would like to see that what does this p plus lambda do to this new wave function, this psi n tilde x. Okay, so let's try to see that what does this do. So here I am simplifying this thing a little bit in x. Okay, now remember this p, these are operators, so p is given by minus I h bar del x. So in 1D this is just a partial derivative, so I can act this thing on this whole part. And then the constant term just gets multiplied with this modified wave function. Okay, so I'll just, in place of p, I'll just put minus I h bar del x. Okay, and you all are familiar with the product rule of derivatives, so I'll just use this product rule. So first of all, this delta x will act on this, and then it will act on this, and there will be summation over these two. So it is like del x. So let me also keep the h bar here also, which will help psi n x plus and then this delta will act on del x psi n x. Okay, and there is the last piece which was there before, lambda e to the power minus I lambda x by h bar psi n x. So let's try to do this derivative. I h bar I lambda x. Okay, so I think, yeah, it should be a minus. There should be a minus here. Yeah, the minus I have missed. Okay, so it becomes minus I lambda by h bar e to the power minus I lambda x by h bar psi n x plus h bar e to the power minus I lambda x by h bar psi n of x. And additionally I had this lambda e to the power minus I lambda x by h bar psi n x. Okay, so let's try to simplify these things. So the first term, this h bar and this h bar cancels, and from two i's I'll get a minus 1, right? Because I is just minus of square root 1, square root of minus 1, so it becomes minus lambda e to the power minus I lambda x by h bar then psi n x plus, so that I will multiply, yeah, okay, that's fine, h bar e to the minus I lambda x by h bar psi n x. Okay, and additionally I have this plus lambda e to the power minus I lambda x by h bar psi n of x. So we can clearly see that this and this are exactly opposite, so I can cancel them, and then I am left with h bar. Okay, I have missed one derivative actually, so del x del x, so it becomes okay, there was also, I have also missed one minus, so minus I h bar e to the power minus I lambda x del x psi n x. Okay, so I can again write this whole thing in terms of the momentum operator. So by that I mean that it can it will be exactly like lambda x, so minus I h bar del x psi n of x. Okay, and you know that this is just the momentum operator, so I'll just write it like x, and yeah, so p of psi of x. Okay, so let me just summarize this thing. So we started with this term plus lambda acting on e to the power minus I lambda x by h bar psi n of x, and we have obtained e to the power minus I lambda x p psi n of x. Okay, this is all right. Okay, so if you, I mean, at any point if you have any doubts, so you can ask me. So now I know what does this p plus lambda operator does to my modified wave function. So I can now try to see, so what happens if I apply directly my h. Okay, so h was given in terms of p plus lambda whole square by 2m, and then there was this additional v of x, and there was this lambda square term which came because I had to complete the square. Okay, so this is my total Hamiltonian. Now I'll act this Hamiltonian on my new psi n tilde x, this states. Okay, so I'll just write the form of psi n tilde first. And remember this psi n here, these are the eigenstates of the h naught. Okay, so now let's see what happens if I apply our h on these psi n tildes. So h has this p square, p plus lambda whole square by 2m term plus v of x minus lambda square by 2m. Okay, now you act this thing on e to the power minus I lambda x by h bar psi n of x. Now as I showed you before, like p plus lambda, how does it act on lambda? It will give you just e to the minus I lambda x, and then you will get a p square by 2m. Okay, so this gives you just the p, and okay, plus, so v, okay, so let me write like psi n of x, and then v acts on this thing. So v is just a function, so it doesn't do anything, it just gets multiplied to this whole thing. Psi n of x, and then there is this minus lambda square which is just a number, so I'll just multiply this as well, lambda x psi n of x. Okay, so let me take these phases out, then it becomes p square by 2m plus v of x psi n of x. Okay, so now see, so this thing is nothing but my h naught. Okay, so h naught psi n x, we already knew that this eigenvalue equation of these are just h e n psi n of x, right? So you'll just use that, but this is, there is a this last term is left, so lambda square by 2m e to the power minus I lambda x psi n of x. Okay, so let's put all of these pieces x, then this term in place of this I'll just directly put e n and psi n x, and then I'll put lambda square by 2m e to the power minus I lambda x psi n of x. Okay, so if you collect all of these things, like it becomes en minus lambda square by 2m, and then you can just take out these phases out because there are no operators anymore. All of these things are either numbers or functions, and then you are left with psi n of x. Okay, so this is the thing that I was calling before psi n tilde x. So now let's see what we started from. So we started from our total Hamiltonian, which is the perturbed Hamiltonian, and we acted psi n tilde. So we acted our Hamiltonian on this psi n tilde, and we found out that this gives me an eigenvalue equation. Okay, so but the eigenvalues for now, because of the perturbation, gets changed, and our en primes becomes en minus lambda square 2m. Okay, and our psi n tilde x's, this becomes e to the power minus I lambda x psi n of x. Okay, so now this, so I mean in this case we could solve the problem exactly, so we did not have to expand those series, expand the series in perturbation. So yeah, this is like one of the very rare occasions when you can exactly calculate the full eigen value and eigen functions. Okay, so is this okay? So like this is the answer that we're looking for. Okay, we have exactly found it. So any question, and so you can ask any questions if you have any doubts. Okay, so I guess then this is clear. So let us move on to the next one. So I mean, see, basically in quantum mechanics there are very handful systems which you can exactly solve, and in most of the cases we will have to go to perturbation theory and do all of this approximate calculation. Okay, so this perturbation theory that you are reading, this thing, like you can do this thing analytically. Analytical means you expand all of these things in the power of lambda and you solve each order by order. Otherwise you can numerically find the exact value. So these are all like numerically you can find exact value and you can match up your this perturbation analytical calculations with that. Okay, so yeah, let us move on to the next one. So this is about particle in the box, and there is an additional perturbation to that. Okay, so in this case we have a symmetric potential well which goes from minus a by 2 to a by 2. So in that case, can do anyone remember that what are the solutions of the eigenstates? What are the eigenstates for this, for a symmetric potential well, symmetric particle in the box? So anybody from the audience, can anybody say what are the solutions in this case? Okay, so okay, so in a symmetric potential well, this solutions, this psi n of x, so these are like they can become I mean depending on what is your n, they are either cosine, so cosine of 2n pi by x, and otherwise it can be 2 by L sine 2n pi by x. Okay, so like this first case happens when n is odd, so yeah, n is odd, and this happens when n is even. So these are the two cases. I mean these are the two, I mean these are basically same. Okay, so I mean normally when you do a particle in a box you do from 0 to a, but here this is shifted, and that's why the sine wave functions they gets changed to either cosine or sines. Okay, yeah. Now in this symmetric potential well, you can define parity, you have evenness or oddness of the wave functions, because see these cosines are even functions, so you can exactly calculate this. I mean you can argue that this x average will become 0, you can argue that this p average will become 0 just from the symmetry of the system. Now so the question is, on top of this particle in the box we have added another potential, a linear potential. So now we are asked to find the change in the ground state up to order of epsilon. Okay, so that means up to linear order, and here this epsilon is my this parameter to which I want to expand this perturbative series. So So let's look at how to do this. So first of all, I'll try to calculate the first order. So first order in En is given by N, V and N. Okay, so now if you write this in this so in the real space, this becomes basically psi n of x star v of x psi n of x minus a by 2 to a by 2. Okay, so now let's insert the form of vx psi n x star. So vx is given by 2 epsilon x by a psi n x dx. Okay, so now you know this psi n's, like I just showed you before, psi n x can be odd or even depending on what is your n. Okay, but psi n x, this mod square, is always even in this case. Okay, so here the solutions are real, so I can remove this star from here. Now I am left with 2 epsilon alpha minus a by 2 to a by 2 x psi n x square. So can anybody tell me what this integration will become? So what will be the value of this integration? So you see, like, this is the even part and this is my odd part. Like, this is just linear in x and we have a symmetric limit from minus a by 2 to a by 2. So that means this integration will become 0. So which implies that after you have added this perturbation which is linear with x, then in the first order the ground state, the energy of any state doesn't change. The ground state energy also doesn't change. Okay, so if that is the case, then you have to go on and calculate the En2s. Okay, so it's the second order correction to the energies. So I'll leave that task for you, but I'll show you another case, so where the first order is not 0. Okay, so the other potential which I am giving you looks very similar, but here this x mod, so here this is x mod in place of x. Okay, so just to remind you, if you plot the graph of this x mod, so x mod is something like this. So this is my x mod. So it is an even function. Okay, so if that is the case, then at the first order it will not be 0, right? So let us calculate that contribution. So again I will calculate the En1. Okay, so here let's just calculate the first correction to the first this ground state. Basically you can calculate this for any state, but let us do for the, just to demonstrate how this is done, let us do for the ground state. So again in this case it becomes 2 epsilon alpha minus a by 2 by a by 2. Okay, so I think this is okay, so this is not alpha, this is just a. Then this becomes dx psi of 1 x, and then there is mod x, then psi of 1 x. So I can just put it 2 in the front and I can change this limit from 0 to a by 2 x, and because we are in the positive region, then mod x becomes just x, and then we are left with the psi 1 x square 0 to a by 2 dx x, and I can directly plug in the psi 1 x. So psi 1 x is given by square root 2 by L sine pi okay, no, not sine. So yeah, this is given by cosine of n pi x. Okay, so n is 1, so pi x by a, and this is also a. So this is my this is my ground state in this system, and then this becomes 2 by a cos square pi x by a. Okay, so that is it. And so I'll just get all of these numbers out. So now the task which is left is just to do this integration, right? So now it is always easier to break these powers of this trigonometric functions in terms of a like single power. So we know that cos square y, so 2 cos square y is given by 1 plus cos 2y, right? So we'll use that formula here. So I am taking 1 2 from this 8 and it becomes 4. So cosine 2 pi x by a. Okay. So now on top of that, let us do a simple change of variable. So let's call this 2 pi x by a as something like let's say y. Okay. So then I'll have to do this variable transformation to this integration. So then 2 pi by a dx becomes dy. Okay, so this dx becomes a by 2 pi dy. Okay, and let's look at the limits. So x has the limits 0 to a by 2. So whenever x is 0, so I can plug 0 here, so y also becomes 0. Okay, so whenever x is a by 2, so I can plug a by 2 here. Okay, so then it becomes 2 pi a by 2 and a. So a from bottom and top they cancels, and 2 and 2 cancels, so this becomes just pi. So this limit is just pi. Okay, so these are my two limits of y. So now I'll plug all of these things in this equation. So now it becomes 0 to pi, and I'll put this dx, which is a by 2 pi dy, and in place of x I'll put y times a by 2 pi, and so 1 plus cos of y. Okay, so now let me get all of these constants out. One plus cos y, yeah. So now this is so I have to do this integration. So before that, let's take care of these constants. So 4 actually cancel from here, here and here, and 2a cancels from here, and then I am left with only epsilon by pi square. Okay, so now let's focus on this integration. Now, so this integration 0 to pi y dy, so you can do this integration. This is just y square by 2 and 0 to pi. Okay, so it becomes pi square by 2. Okay, so the first part you can do easily. for the second part you have to do something called integration by parts. So let's do this. 0 to pi dy y cosine of y. Okay, so in this case I'll write this cosine y as d of so I'll directly write this as d of sine y, or okay, dy and there will be a yeah, there will be no other signs. So then you can write this, you can do just integration by parts, then this becomes y sine y, put the limits 0 to pi minus sine y, and then this is just dy, right? So yeah, this is it, I guess, and you put the limits here. So the first term will give you so pi times sine pi. Okay, so both of sine pi is 0, and then 0 times sine of 0, then that will also give you 0, and then this integration will give you cos y, and additionally plus, and then you are left with z pi and 0. Okay, so at cos y at minus pi is given by minus 1, and at 0 it is also 1, so you get minus 2. Okay, so I guess I have not made any mistake here. So now you can take this calculation, and now this whole equation, this becomes 1 plus pi pi square by 2 minus 2, yeah, something like that. So you can take the calculation. I hope this is okay. So any question until so here? So this is my first order correction to my ground state. Okay, so is this okay, or any clarification? Do you need any more clarification? You can just let me know. Yeah, okay, so let us move on to the next problem. Okay, so yeah, this is somewhat interesting, so let's look at this problem. Okay, so in this problem there is a particle with charge E and mass m, and this is confined to move on a circle. Yeah, so on this circle with radius r, so it only moves along this. Okay, so for that the Hamiltonian is given by this Lz square by 2mr square. So here this 2mr square, this is yeah, okay, so like this is what you get when you have this only rotational kind of kinetic motion. So here this whole motion is confined into the plane, so you have only one of this z square. Okay, and this you also get this mr square, which is like, so this part is like the moment of inertia. Okay, so this is how you write any rotational kinetic energy. So this is your total Hamiltonian, there is no other potential. So in this case you can study this problem, and you can try to solve it. Solution of this is very easy. You try to plug in something like this, some solution like this, and then you will find out that this will give you this kind of energies when you will demand that this psi n at phi should be same as psi n at phi plus 2 pi. Okay, so that will give you the quantized energies. Okay, so if that is the case, then okay, so I forgot to copy the rest of the part. Okay, yeah, now let's say this is there is an electric field which is applied on the plane of the circle. Now you are asked to find out the perturbed energy up to order of energy square, E square. So this E here is the this electric field, the magnitude of the electric field. Okay, so this acts as a perturbation in this case. So electric field is very small compared to these energies. In this case, then only you can do perturbation. So that is the case here also. So now we are asked to calculate the energy, perturbed energy up to order of E square. So now, so the first plan is to get the E1s, right, for any n. So E1s for any n will be given by some n, v and n. Okay, and this v of r in this case for this constant electric field is given by something like this, er cosine of phi. So I am assuming here that E vector is applied to this E and I cap, and then you can just calculate this first order correction in the energy. It becomes something like this. Star, and you plug in ER, E minus ER cosine of phi, and then psi n phi. Okay. Yeah, there is another integrations because this is on 2D, and so there is a circular symmetry in this problem. So now we would like to use that, we would like to exploit the symmetry, and we will use plane polar coordinates. So now this integrations becomes r dr d phi. Okay, now this phi goes from 0 to 2 pi, and r goes from r is okay. So r in this case is just constant, so I do not need this part as well. R is just a constant. Yeah, this is just an integration on phi. So yeah, now you look into this and you just plug in the forms of the wave functions here, 0 to 2 pi, and there is psi n. Okay, psi n's are nothing but 1 by n e to the power I n phi, c to the power I n phi, and there is cos phi, and this e times r, these are just constant. I will just add one minus. So you see this becomes 1, and then there is just one integration with cosine of phi. Okay, so you all know that cosine of phi, or any periodic function which has a average 0, that becomes 0, so cosine also becomes 0. So the first order correction in this case essentially is 0. Okay, so then you have to look forward the second order correction. So en2. So en2 will be given in terms of like matrix elements of this V. So then we will have to calculate some things like V, n and mth component of V, and En minus Em, there is a summation over n not is equal to m. Okay, so before that, let us first try to understand what are the other matrix elements. Like for the diagonal elements, we have seen that which gives the first correction, so this is 0. So we are sure that there is no diagonal elements, but let's look at some other elements of the matrix itself. So in this case also, I'll just write this in real space. Phi. Yeah, okay, so I have been missing one r. Yeah, so there is one r. So r is the radius of this this circle. So r d phi, and then there is yeah, so then there is e to the power. Okay, so let me first write this psi as psi n star phi, and Vr is minus Er cosine of phi, and then I have psi m phi. So I'll simplify this. I'll just take all of the constants out, and I will additionally have square root n and m okay, not square root nm, yeah, square root 2 pi. So this is just 2 pi. So here also it should be 2 pi, 2 pi. So now there is 2 pi, and then we are left with e to the power minus I n phi, e to the power I m phi, and cosine of phi. So let us see that whether this is 0 or not. So now this becomes m minus n phi, right? Now you can also expand this cosine in terms of this exponent e to the power I phi's, right? So cosine has the expression that this is e to the power I phi plus e to the power minus I phi by 2. Okay, so this is the expression of cosine in terms of this e to the power I phi's. So then there are only two terms. So 0 to 2 pi, and then there is I m minus n plus 1 phi plus e to the power I m minus n minus 1 phi, and you divide the whole thing by 2. Okay, so I will take the 2 outside. So this is the integration now we have to do. Okay, so any idea what this integration will be? Any idea, anybody? So see, these are exponentials, right? So I mean, these are just phases. Okay, so if you have any phases and you do a integration over the whole 2 pi, that will generally become 0. Okay, so when when this thing can be non-zero, so only the case if these phases are actually 0, then only it will, the whole integration will give you non-zero, right? So when this will be 0, like, so e to the power some 0 times phi is just 1, so then the integration will be 0 to 2 pi, this will give you just 2 pi, right? So when that is the case, so that will be that will happen when m will be m minus n plus 1 is 0 for the first term, and for the second term this integration will be non-zero when this m minus n plus 1 is 0. Okay, so now this integration, like this, it can be 0 or non-zero depending on what are the values of f and m and n. We can write these values very simply using the Kronecker deltas. So this is given by 2 pi Kronecker delta m comma n minus 1, and there is additionally delta m comma n plus 1. So this 2 and this cancels, so this becomes 2. So now this is your whole answer for the matrix elements in V M. Okay, so now you see that we have not assumed what are this mn. So mn can be any integers, any states of the system. So when we want to calculate this, let's say E2 of nth state, so then we'll use this expression n v m en minus em, there is a mod square in this, and summation over n not is equal to m. So this thing you can write for any m. So this will become e square r to the power 4 by 4, and then there is like delta m n minus 1 plus delta m n plus 1 whole square. Okay, and there is a summation over n comma m, and n not is equal to m. Okay, okay, and there is also so let's remember what are those eigenvalues of this system. So the eigenvalues are given by h square n square by 2m r square. Okay, so let us go back and plug those things as well. So h bar square n square by 2m r square minus square m square by 2m r square. So I will take this constants also common from this expression. It becomes 2m r square by h bar square, and then we are only left with this summation delta m comma n minus 1 plus delta m comma n plus 1 whole square and n square minus m square. Okay, so let's I hope this is okay. Yeah, seems to be okay. So then this becomes e square r to the power 6 m, so 4 h bar square. Okay, so it is a good idea to take these calculations yourselves as well. So I can just open up the square plus there will be delta m n plus 1. So the square of this delta function are also like, these are like so any Kronecker delta m comma n, if you just square it, it becomes just delta m comma n. Okay, so these are the special property of Kronecker delta, and any other cross term goes to 0 basically. So because that will imply two conditions which cannot be satisfied in a same for the same m of m and n. So you can do these summations over now n and m. So let's say we sum over m. So now it becomes 1 by n square minus n minus 1 square plus 1 by n square minus n plus 1 whole square. Okay, like I've used the property that when the Kronecker delta is not 0, so I am plugged into this denominator and then I have found this. Okay, so now you can go ahead and simplify this equation even more and try to find out the final expression for yourselves. Okay, now this is the only task is left to manipulate, do more simplification and find the answer in a compact form. Okay, so now this will give you the second order correction. So in the second order, you see the e actually appears as a square. Okay, so that's why this is second order correction. Okay, and this is the first non-zero correction in this problem. Okay, because the first order is already 0. Because the cosine integral over a whole 0 to 2 pi, that becomes 0. So is that okay? Any doubt? So you can also look at these notes later on. I will upload them to the designated folder which you will have access to. Okay, so in case if you don't understand something, you can look into that at your own time. Okay, so let's go on to the next problem. Okay, so now we'll be doing a perturbation calculation using matrices. Okay, so now you are given a system which can be represented by a 4x4 matrix. So you can think of this like we have a 4-level system. Okay, so 4-level system can be represented by a matrix of 4x4. Okay, so now if there are no off diagonal terms, then we know exactly that only 5 minus 5 5, 8 and minus 8 would be the eigenvalues. Okay, but if there are additional lambdas, additional off diagonal terms, then we cannot always find those eigenvalues exactly. So here we'll try to because these are block diagonal forms, so these are basically 2x2 matrices, so we can find the eigenvalues exactly, and we will also calculate the perturbative corrections and we will try to match those up. Okay, this will yeah, so we will basically match those up and see whether how much they agree or not. So like first of all, I can break this Hamiltonian apart into two parts. So H can be written in terms of H naught plus our this HP. Okay, so H naught in this case is given by minus 5, 5, 8 and minus 8. Okay, so all rest of the terms in this case are 0. Okay, so now if I have a diagonal matrix, I can find this eigenvalues of this diagonal matrix very quickly, because these are just the entries of the diagonal. Okay, that will give you the eigenvalues. So eigenvalues are minus 5, 5, 8 and minus 8. Okay, and the corresponding eigenvectors in this case, they are just very as simple as 1, 0, 0, 0. 2 is given as 0, 1, 0, 0. 3 is given as 0, 0, 1, 0, and 4 is given by 0, 1. Okay, so this is the whole eigenvalue and eigen states of the H naught, okay, which is a diagonal Hamiltonian. And now the HP, we have to add this HP and we will calculate the eigenvalues again. And we will see that what are the changed eigenvalues of this system. Okay, so HP in this case is given by 0, 3 lambda, 3 lambda 0, 0 minus lambda 0, 0, 0. Okay, now so this is my HP. Okay, so first of all, let us try to find the eigenvalues of this H plus HP exactly. So H plus HP is given by minus 5, 5, 8 and minus 8. So this entry is 3 lambda, 3 lambda, this is minus lambda, and this is a 2 cross 2 0 matrix. Okay, so whenever you have block diagonal, so like this is a block diagonal. Okay, so you can separate each of these blocks out. So whenever you can do that, you can look into this smaller blocks. Okay, and you can find the eigenvalues, and they will give you the eigenvalues of the whole system. So for example, so you can look into this smaller part, minus 5, 3 lambda, 3 lambda, 5. Okay, so for this smaller matrix, let's calculate the eigenvalues. Okay, so to calculate the eigenvalues, we have to solve something called the characteristic equation, which is given by this determinant of this matrix. Okay, so this becomes minus 5 plus E, 5 minus E minus 9 lambda square. Okay, so now let us solve for energy E. All right, so yeah, this is okay. So this is eigenvalues of the first block, and for the second block, let's calculate as well. So the characteristic equation will be here similarly given by this equation. Okay, so now this is again 8 minus E, 8 plus E and minus lambda square. So it will become 64 minus E square minus is equal to lambda square. E square minus 64 will be minus lambda square. E square will be 64 minus lambda square. So E directly, let's write directly, E is plus minus 64 square root 64 minus lambda square. All right. So this is the energies of the perturbed Hamiltonian, like H plus HP. So here this is because this is a block diagonal, and each equation, each characteristic equation is a quadratic equation. So we can find the eigenvalues here exactly. Now let's do one thing. So first of all, let's list these solutions. So so I have 4 energies. Okay. So plus minus 25 minus 9 lambda square, and plus minus 64 minus lambda square. Okay. So first of all, let's also expand this in terms of the lambda. Okay. So you might be familiar with the fact that if there is some 1 by x square root, then this, if you expand it for small x's, like x is much less than 1, it becomes 1 minus half x and plus so on. Okay. So I'll just expand up to first order. So now this thing becomes plus minus 5 1 minus half 9 by 25 lambda square, and in the second case it becomes plus minus 8 1 minus 1 by 2 times 64 lambda square. So let us just simplify this just one step. Plus minus 5 plus minus 5 minus 9 by 10 lambda square, and plus minus 8 minus 1 by 16 lambda square. Okay. So yeah, so okay, so there is no first order in this case. So there is, because this is lambda square, so this is my series up to lambda square. Okay. So I can write o to the power lambda to the power 3. So this series is valid only up to square. Okay. So now this is so I'm going backwards. I have the exact solution of the energies. Now I have expanded this up to lambda square, and from the perturbation theory also we can calculate the same quantity, right? So the same quantity in that case will become like H, so E2, okay, it will become just N HPM mod square, and En minus Em, and summation over n not is equal to m. Okay. So these m's and n, these are the eigenstates and eigenvalues of the bare Hamilton, this H naught. Okay. So you can plug all of these values and you can check yourself that this whole equation will be same as these two equations. Okay. So I'll leave this task for you. You can check. So this should give you exactly these two quantities. Okay. So yeah, and I'll discuss one last problem which is very interesting and which will help you to solve your assignments. Like, so there is a problem where you are asked to calculate expectation values of 1 by r square and so on. So yeah, so for that I want to just discuss one small problem. So this is more like a theorem which is called Feynman theorem, and through which you can actually so this is kind of a trick in quantum mechanics, so with which you can calculate some expectations values without doing much calculation. So this is to say that, let's say you have an eigenvalue equation, and in that eigenvalue equation you have a parameter alpha. Okay. So H alpha, and then there is U alpha is given, so E of alpha and U of alpha. So because Hamiltonian depends on that parameter alpha, then all of the eigenvalues and all of the eigenfunctions actually depend on alpha as well. Okay. So this U alphas are the eigenstates of this H, and E alpha is the eigenvalue for the U alpha H state. So we can write n also, we can mention n also, but which is not necessary right now. So now I want to calculate del E del alpha. Okay, del yeah, so this thing. So this thing is like I know the expression for del alpha, right? So del alpha, yeah, I know the expression for E alpha, which is given by U alpha H of alpha and U alpha. Okay, and so now this actually acts on each of these parts. Like I mean, this acts on this part, and this part. Okay, so you have to apply product rule thrice. So then the first term becomes del alpha of U alpha, and then the second term becomes U of alpha del H alpha del alpha U of alpha, and then you are left with only del alpha acting on this gate. Okay, so so you see that so I want to prove this quantity. Okay, so I almost have this quantity, right? So this is my del H alpha del alpha expectation. Okay, but there are two other pieces which are hanging here. So how do I get rid of them? So now to get rid of them, you just notice that this U alpha and U alpha is actually 1. Okay, and then if you take some del alpha of this U alpha and U alpha, this boils down to 0, because 1 is constant. You cannot take derivative of a constant, right? That becomes 0. And then if you just apply the product rule here also, you will see that this quantity, like this two quantity, I mean, will just emerge out of this thing. Okay, so here before doing that, you can also just substitute this eigenvalue equations like Ens, and here also you can substitute the eigenvalue equation, and you will find out that this and this goes to 0. So which means you are left with only this quantity. Okay, so this is something called Hellman-Feynman theorem. So what are the applications of this? Like why are you even doing this? So like let me give you two small examples of why you can use this. So let's say you have the harmonic oscillator. So in harmonic oscillator, the Hamiltonian looks like p square by 2m plus half m omega square x square. Okay, and you know the solutions, this energy, they just become n plus half h bar omega. Okay, so now let's say I am asking you to calculate x square for any nth eigen state. Okay, so if you want to explicitly do the calculation, that calculation is not so easy. Like there are Hermite polynomials hanging around, there are Gaussian functions hanging around, then this whole quantity calculation becomes not so much trivial. Okay, it becomes somewhat rigorous. So what we can do is, so let's take omega as parameter. And then we will take derivatives with respect to omega on both of these sides. Okay, so like the first term becomes m omega x square. So like this term comes from here after taking a derivative. Okay, and then I will take the derivative here also with respect to omega, then it becomes n plus half h bar. Okay, and this first term, this doesn't actually depend on omega, so it will not survive when you do the partial derivative. Now after doing this, we can take an expectation value on both sides. Okay, but on the right hand side, this is just a number, so expectation value doesn't make any sense. It becomes, just expectation value will give you this times 1. Okay, so you can extract out this m omega, this constants, from the left hand side, and it becomes x square average, and on the right hand side you get n plus half h bar. So let me bring this m omega down. Okay, so like let's just see this with how small calculation I could find out x square average for any general state. Okay, so like this theorem is a very useful theorem. Okay, so let me show you another example. So like in your assignments you are asked to calculate the expectation value of 1 by r for the harmonic for this hydrogen atom, right? So let's try to use the Feynman theorem to do it very easily. Okay, so like in the hydrogen atom, so I am writing this as some h naught plus there is e square, the Coulomb interaction term, 0 r, and the rest of the terms are inside this. Okay, I am not interested about this because at the end of the day I'll take the expectation value, I'll take a derivative with some parameter, and I am saying that this h naught doesn't depend on that certain parameter. So now this thing I can write in terms of h naught h tilde square minus m c alpha and r. Okay, so this alpha here is a fine structure constant. Okay, and if you find the eigenvalues of this whole thing, this will give you something like I think it is c square alpha square by n square, and there is probably some m square here. Okay, so yeah, this is I think this is the basic form. Yeah, probably yeah, this is, I think this is correct, or let me write something like that. So I'm not sure what the other number is, so I'll just write it as a lambda. Okay, capital lambda, and so I now take alpha as a parameter. Okay, and we'll do a partial derivative with respect to alpha. So now from the left hand side we will get m c by r, and from the right hand side we will get minus lambda alpha by n square. Okay, so now after doing this I'll cancel the minus from both hand side, and I'll take expectation, and on the right hand side there is only a constant number, just a number, so expectation gives you just 1 times that number. So 1 by r expectation 2 gamma alpha m c by n square. Okay, so basically this is your expectation value of 1 by r. Okay, so I'll just show you this this thing, how to calculate for 1 by r. So you can go ahead and try to calculate this for 1 by r square, 1 by r cube, and you can see that what you get. Okay, so yeah, so that will be all for today. So any question, any doubts? So if there are no doubts, then yeah, so you'll have access to this video also in YouTube. So I guess we'll meet next week then, and have a good weekend. Okay, so yeah,